Okay, so let's continue. I will just give slight examples on that, but before that, it's not always possible to find maximum likelihood estimators by differentiation if Emily occurs at the boundaries, occurring at boundary of the parameter space. Usually when the range of x depends on parameter like uniform 0 theta or double exponential. So we have this problem. Basically we cannot obtain the maximum likelihood estimators by differentiation because maximum occurs at the boundaries in that case. So we have to use inspection method actually in that case. So we will see how to do that. So we cannot obtain by differentiation. And in this case, basically we can use inspection. So actually, in most of the case, our likelihood function has this shape, and then we can get, so this is, let's say, is our whole parameter space, and we obtain theta hat as the maximum point of the likelihood function. Okay, so the theta hat will be the estimator. So here, if this is the case, we can obtain this point basically by using the obtaining this by differentiation. Okay, so here when we take the derivative of likelihood function equating to 0, we obtain it. But sometimes our problem, especially when the range of x depends on the parameters, so we have this type of shape. Okay, so and let's say this part is our whole parameter space. So our basically, so this goes till the infinity. Okay, so we cannot find the maximum point in this case. So here theta hat is the question mark. So here maximum obtained at the boundary. So we cannot obtain here it by the derivative method. Obtained at the boundary. So not obtained by differentiation. Okay. So we will see the methods basically. Okay, so when we have more than two parameters, so the method can be generated to more than one parameter case. Okay, so when we have a random variable x with the given PDF with unknown parameters theta 1 and theta 2, so our parameter space basically defined by these two. Okay, so we want to find theta 1 hat and theta 2 hat. So we want to find the likelihood function of theta 1 and theta 2. So this is basically mathematically the joint PDF of theta 1 and theta 2. So get the maximum value of the likelihood function for these under the parameter space. Then from here we can get theta 1 hat and theta 2 hat. So again we are using the same logic basically. Get the likelihood function, take the derivative, equate it to 0, and do the same thing for the theta 2. Equate this to 0, and then solution of these will give us theta 1 and theta 2 hat. So here, since we have a two unknown parameters case, we have to check these gives us the minimum values or maximum values. So in that case, we have to check the second derivatives. So theta 1 square. and multiply this by, so when theta 1 hat and theta 2 hat replaced, multiply this by the likelihood function theta 1, theta 2, second derivatives, again theta replace theta 1 hat and theta 2 hat, minus the partial derivatives, derivative of these, take the square. If it is positive, then these scores theta 1 and theta 2 hats gives us local maximum values. Okay, so let's look at an example, then I will finish today. Next time I will continue with more examples. Okay, so let's say we have an exponential PDF and find the MLE of theta. So procedure is very easy actually. So you will see we take a lot of time to understand the likelihood function and why we need to maximize the likelihood function. So I'm using this form of the exponential PDF. Okay, so theta is positive. Okay, so find the likelihood function. So it is same as the joint PDF actually. Theta, so 1 over theta to the n, e to the minus summation xi over theta. So if you have some problems with finding the likelihood function, sometimes you don't write xi, so sometimes I'm seeing that, so you are writing this as n times x, okay, so it's not like that. So you can write this as n times x bar, but you cannot write it as n times just x, okay. So if x, when we have a sample, which x I have to use? First one, second one, third one. So it should be a function of some random variables. Okay, so put that. So here you have to replace each x by xi, x1, xn. So you forget about that and then just multiply it and then write nx. So be careful about that. Okay. So then let's find the log likelihood. Okay, then take derivative of the log likelihood function with respect to theta. Equate this to 0, and so for, let's forget summation xi over n. So this is an estimate, then our theta hat should be x bar. Okay, so check this point, it maximizes the likelihood function. Okay, so take the second derivative, replace theta by theta hat here. Okay, and then we get n over theta square minus 2 times summation xi over theta cube. Again, replace theta by summation xi, so we will see that we will get minus n over x bar square, which is negative. So this means that this theta hat value maximizes the likelihood function, so it is the MLE of theta. Okay, so this maximizes the likelihood function for the given sample. So instead of theta, I can use x bar. Okay, so it maximizes the likelihood function for the given sample. Okay, then let me stop, and next time I will start with continue with more examples, and then we will see some advantages and disadvantages of maximum likelihood estimations and some properties of maximum likelihood estimators. Then we will start to seeing some good properties of any type of estimator. Okay, see you next week, or actually see you on Wednesday.